architects.
Okay, welcome everyone for this new design exercise powered by Aviatrix. I am Maxime Derat. I am a principal solution architect in Aviatrix, and I'm based in Brussels. I'm part of the EMEA solution architecture team, where we help our customer to best architect their cloud network and security infrastructure based on their needs, challenge, and requirements. I am your host today with Gerald. So Gerald, could you please introduce yourself?
Sure, thank you. Good morning also from my side. I'm Gerald Buchholz. I'm also a principal solution architect in the EMEA team for the solution engineering team of Aviatrix. I live nearby Munich in Germany, and I'll walk with you through the design backgrounds on this design exercise that we are going to do today. So let's get started with the design exercise for cloud architects. As you might have heard before, today this design exercise is about a SaaS provider that is bringing software to his customers, and this is the business background of the company. So we're talking about the company ABC, which is a software company for manufacturers. So their software, they're offering a software as a service that helps customers to optimize their production workflows in their shop floor. So they have a deep integration with their production environments and optimize the way how the production is done. Since this is integrated in the shop floor environments, you can imagine they depend on the software of ABC and of their availability. Of course, they can still produce things that if they lose connectivity, but for sure there'll be a revenue loss due to inefficiency that the software usually in the background does to optimize the production here. Today, they have roughly 70 customers, and they plan to extend that customer base in the next 18 to 24 months. So they want to reach roughly a customer base of twice the size they have today. So it will be roughly 140 customers they are planning to have in the next 18 to 24 months. Recently, they discovered in their environment that due to access to some malicious websites, they caught some crypto miners that were running on their VMs and their existing cloud environment. So this is something which didn't harm their production environment, but it caused them some problems due to the CPU loads that these crypto miners used. So this was a problem that they identified, they solved it, but they want to be sure that they don't have anything else, or that this is prevented in the future. Today, ABC is only running their software as a service in Azure. So this is based on infrastructure as a service. So VMs that are based or located in Azure, and they're just having a single region in availability zones, but just in a single region. For resiliency, they plan to add and deploy AWS or resources in AWS, so that they can even overcome an outage of the complete environment of Azure. So, for example, if the whole region goes down or is not available, so that they have a recovery or failover region or failover geo in AWS. We don't need to take care of this resiliency in this architecture session or design session. We need to the software itself will take care of the failover. So it will choose what's the best available cloud or where's the service actually running in, and then will fail over to the other cloud that is the backup cloud here. So in this case, AWS. More and more customers are also mandating them to offer dedicated private connectivity, because they want to have a guaranteed SLA on the connection between on-premises and the software that runs in the cloud. So they want to ensure that they have an SLA here and can also get a low latency here. Today, the customers are only using VPN connections, but this will change in the future. So let's go to the technical side and the requirements they have from a technical standpoint of view. They require customers to use IPsec to connect to the cloud. So they don't want to have any issues regarding unencrypted protocols they might use or where they fall back. So they decided to only use IPsec connectivity to the cloud. Some customers might be connected to AWS, while others might be connected to Azure. So there's no mandation from the customer or from the company for their customers to actually oblige them to use a special cloud, so customers can choose on their own. They already identified and have challenges with overlapping IP addresses. So customer C might overlap with IP addresses from customer A. They're also planning to move their own data center from on-premises to AWS. So they'll consume later their own services directly from AWS. They already have a footprint in Azure, but their data center migration will go to AWS. Recently, and they decided to use a direct connectivity here. That's also good to mention here. Recently, they had a problem that a customer of them that did BGP between their on-premises routers and the VPN devices in Azure did some misconfiguration in the BGP and announced a route which caused some problems for other customers so that they couldn't reach the services anymore. So they want to control how the routes are propagated towards Azure and towards AWS as well to ensure that there's no outage if there's a misconfiguration on the customer side. Also, they want to isolate the traffic. They want to ensure that only certain customers can reach, for example, the pre-prod environment, for example, for beta testing, while others only have access to the prod environment. Still, they need to ensure that they all can connect, that the company itself and the developers can connect to all environments to do their work so that they can actually develop in the different areas and, for example, have access to the areas or environments when they're doing troubleshooting. Important again, customers cannot communicate to each other. So customer A cannot communicate to customer B or C. Another thing that they want to achieve is that they get deep insights into the network and into the connectivity. They recently had some problems which were not binary way. They were actually not pure connectivity. It was something where they experienced higher latency and they had really problems finding the solution of the problem at the root cause to solve it. So they need more visibility for troubleshooting and daily operations. Again, all traffic must be encrypted. They chose IPsec for encryption. So every traffic that enters the cloud or leaves the cloud must be encrypted via IPsec tunnel. To avoid unwanted communication to the internet, they want to implement an easy solution to actually allow software patches for their VMs while stopping them communicating with unwanted services. So that are actually the technical requirements that they have today. So how does the current design look like? They have their services today deployed only in one Azure region. It is, for this case, West Europe. They're planning to adopt AWS and deploy also services there. Besides network security groups, there are no additional filtering mechanisms in place. So everything is done today on NSG level. So for example, if customer A wants to communicate to the prod environment, they're going to allow this on the on the NSG and give the customer access to the certain workloads he needs to have. Due to the existing solution they use with Azure native VPN gateways, they have only limited NAT capabilities. So they want to get beyond that and want to have more advanced capabilities when it comes to NAT, to also have control over more sophisticated scenarios. And they recently discovered that when they want to go beyond a certain tunnel limit, they need to upgrade their VPN gateways to a certain size. And then they already hit another limit, which is 100 tunnels that what they can't get beyond that. So they need to find a solution also for having more than 100 tunnels towards the cloud. As we remember, they're planning to have at least 140 customers in the next 18 to 24 months. So this is something that is coming across sooner. So what is this design exercise all about? So when we look at the nice example that we're using here for a quite decent building, you might realize it doesn't look like what you would expect from a real architecture that is behind it. Of course, you can live in that house, but you'll sooner or later get annoyed from many things. For example, if you look at the windows, some of them are quite difficult to open, and others doesn't make sense to open at all, because what shall they bring here? And how you get to the handlebar of this window, for example, or how you're going to open the garage. Yeah, all these things are not very good in this architecture. Although you can live in this house, you might get not only annoyed, but you will start sooner or later to realize that that there are many burdens with it if you live in that house. And this is exactly the same what we're talking about at Aviatrix. We're talking about a good architecture, because we see that you can use native constructs to build multi-cloud environments, but there are many walls that you will hit when it comes to, for example, to connectivity or to troubleshooting that might be not good at all to really do it on a daily basis. So architecture is key. So it is very important for us to get a common architecture that leverages best practices across multiple clouds, not only within a single cloud, and that makes the deployment, maintenance, and operations across multiple clouds as easy as possible. So this is why we invented the multi-cloud network architecture, which is based off 3 basic pillars. The core pillar has 2 layers in it. That's the cloud core, where we have an application layer where you're going to connect your virtual data centers to. So it's your VPCs, your VNets, or your VCNs in Oracle, so that you have your workloads living in the cloud that is connected with the virtual data center to the global transit layer, which allows us to connect within the clouds within a cloud across multiple tenants, but also within multi-cloud environments. So use cases are quite exhaustive here. As mentioned, it is not only about multi-cloud, it's also about single cloud multi-tenant architectures, which can get quite cumbersome because there are some limitations if you're going to deploy such architectures here as well. The global transit layer is not only available, again, for a single cloud, it's also multi-cloud. So if you span across the clouds and you're going to add multiple clouds here or additional clouds, then you'll realize that it is simply across the different clouds, because you're always deploying the same architecture in the same and the same building blocks across different clouds. Also in the transit layer, we integrate things like the authentication if you use a user VPN, but also the authentication to controller and Copilot, where you can add your own identity provider like Azure Active Directory or integrate, for example, with Okta. Also, one important thing, we have a zero-touch provisioning for certain firewall vendors. That doesn't mean we only allow that firewall vendors, but we have a zero-touch provisioning with Checkpoint, Palo Alto, and Fortinet, so you can simply deploy these firewalls in the transit layer and they'll be integrated in the routing, and you don't need to take care of reading any 500 pages books for each cloud, for each vendor. Instead, this is completely integrated into the multi-cloud transit and adds it there. The cloud access is building the part where you connect from on-premises, where you connect user VPNs, for example, or where you're going to add egress from other services to this egress and ingress from other services to Aviatrix and then to your workloads. So if you deploy, if you start to deploy, you can apply the same building blocks that you have across different clouds. So the architectural pattern will look different. It will look similar to all clouds that you have. And then you're adding the multi-cloud connectivity to it, the multi-cloud transit, and then you can reach, in this case, for example, from AWS to Azure and from Azure to Google, but also from AWS to Google. So there's a ubiquitous architecture to reach all clouds, not only a single cloud here. The other pillars that accompany the central pillar is the cloud security pillar, where we say secure everything. So we are going to take care of, or we're going to give capabilities to secure in and egress traffic. We're giving you access control towards the platform, but also towards your workload. And we also add things like encryption here, where we encrypt everything. And to add the last bullet point here to make it a round solution, we also give you segmentation possibilities, so you can segment your traffic and say, okay, I don't want to talk workload A with workload B or customer A with customer B. Of course, when we're talking about a nice architecture, you also need to think about how do I maintenance there, and that is actually the global visibility and control that you have on the left side, the cloud operations, where we're giving you the tools to do the troubleshooting, see the trendings in your communication patterns, give you access into give you insights into your communications patterns, where you see who's talking with whom, but also helps you with the appropriate troubleshooting tools if you got any problems. For example, A cannot talk to B to see where is the problem lying. Aviatrix will analyze the underlying platform and give you the needed information to do a meaningful troubleshooting across your environment. So with that, I'm moving on. Sorry, I'm moving on to the design exercise itself. So we're now talking about cloud native with a third party. Where are the differences, and how would you design such a solution with the existing tools that you got from the cloud service providers, in this case, Azure and AWS? So who would like to step up and design with me a solution that fulfills the requirements that we have from customer ABZ to bring his software to his customers? Anyone wants to step up here and start to design with me?
Gerald, Maxim, if last call, anyone is interested to design with Gerald with native construct and third-party construct? Please, this is your session. It has to It has to be a bit interactive, so do not hesitate to step up. Not
It's your
okay.
chance to design with me.
So Gerald, if anyone is interested, I am interested.
Great.
And I will try to make an architecture with you with the cloud native and third-party construct. Is that okay?
Yes, please go ahead.
Okay, so with that in mind, I would build in the transit layer for Azure an Azure V1, virtual one, which is to me the transit construct in Azure. And I would do the same in AWS with the, oops, not this slide.
Sorry, yeah.
No problem. Yeah, and I would do the AWS transit gateway for AWS.
Okay, so you would paint something like this, a virtual one.
Yes.
Okay, and
that
here you're
would
going
be
to have
my core layer for the two public cloud. And then for V1, I would do some up connection to the Spoke VNet.
Okay, yeah, great.
That way, I link my application layer to the transit layer. And I would do the same for AWS. This is called TGW attachment to the VPC. So that way, the two layers are linked. Then for the access layer to the customer, as these are private connection, I would do, I would spin up an express route gateway and link it to the express route to the customer.
Yeah.
And for the TGW for AWS, I would configure a DX Connect gateway aggregating the DX connection and link it to the data center and customer B, with the thing in mind that for the data center, this is a 10 gig link, so high-speed connectivity. So
great,
yeah, and a link to the data center as well. Yeah. That way, let's say I have my connectivity.
Yeah.
Now,
sounds good.
For the routing control requirement number 2, to be honest, I do not have a big solution in mind. So what I would do is to control the routing at the customer side, meaning that these are BGP sessions between these things. So I would configure, for instance, a route map, you see, and I would filter the advertisement of BGP with the route map as an example. That would be my solution to requirement number 2. Requirement number 3, end-to-end encryption in the cloud and to on-prem. When leaving the cloud, let's park for later. I do not have a solution in mind.
Okay, great. Yeah, sure.
Requirement number 4, overlapping. Again, I know that V1 and TGW do not have advanced NAT capabilities. So again, I would ask the customers to do some NATing for me.
Okay, so we're going to add that as well.
Especially for customer A and C, because B is not really involved in the overlapping. So I would ask customer A and C to do some source NATing to transform the 1016.1/24 to something else, to another RFC 1918. Okay,
that's a way to do it. Yeah, sure.
Yeah, for requirement number 5, I'm a bit more knowledgeable in AWS, so I will start with AWS. I know that with the TGW routing table, I can segregate my traffic. So it means that I will do a routing table in TGW for the production spoke. I would do a second TGW routing table for the dev spoke. I would do a third one for the data center and a fourth one for the customer B in AWS. Okay. And for V1, I assume that maybe the same concept applies.
Well, in V1, you have something where you can use labels to propagate routes across different spokes.
Okay.
And
okay.
this is something you can
Sure.
apply here. It's a little bit more difficult to implement, but it's technically possible.
Right. Okay. Requirement number 6. Oh, sorry.
Sure, please go ahead.
Requirement number 6, egress internet control for the private workload. So what I would do, and I will explain you the rationale behind, I would spin up some next generation firewall in the transit layer for both public cloud. Right. That way I can filter my egress internet bound traffic from the private workload to internet. I think
okay. Yeah, sure.
It could meet the requirement.
Sure.
And for requirements 7 and 8, protection against the crypto mining, I would use as well the next generation firewall that could meet that requirement. And for the multi-cloud visibility, I do not have a multi-cloud visibility tool, but I would use, for instance, the Azure Network Watcher for Azure, and I would use VPC Flow Log and the route analyzer in the network manager for AWS. These are multiple tools, but maybe with the addition of all these tools, I could get something in for the visibility requirement. And that would be my architecture with cloud native and third party. What do you think?
Well, it meets partly the solution. How do you connect the both clouds to each other? Do you have any solution for that?
Yes, good question, Gerald. Thanks for asking. I would do an IPsec between the next generation firewall.
So something like this.
Right.
IPsec. Okay. Well, let's take a look at what the requirements were and how they were met. Okay, we had prod dev and we had a prod and dev environment in AWS and Azure. Okay, we had the customers A and B connected via A and C connected via an express route. That's met. Of course, we also met the customer connectivity for customer B via direct connect, and also we could connect the data center from ABC towards the direct connect gateway. I think that's something where we can say, okay, this is met. Incoming need for routing control for incoming routes from customers. So this is, from my point of view, partially met because we depend on the customer. We have a raise of hands. So okay. Regarding the end-to-end encryption at network level, you said that you're going to have an IPsec. Well, I think we didn't come across the end-to-end encryption. One way to do it.
I do not have solution between the spoke and the transit, to be honest.
Yeah, one way to do it with native would be if you're going to between the spokes and the transit. That's true. There's no good solution here. But if you're just looking at the solution to encrypt via on-premises, you can build an overlay IPsec going from the on-premises router through the ER to the IPsec gateway in Azure. Me not being an AWS expert, I don't know how this can be handled in AWS, but I assume that you can do some similar and have an encryption via IPsec within AWS, but I think it will be quite cumbersome. So this was something that were not met in the first place. So this is partially met. This is not met from the beginning, but okay. Regarding the
sorry, just Gerald, a second. I believe Paul, you raised the hand. Did you want to make a comment or ask a question? Now you have the ability to unmute yourself, Paul. So speak up if you will. All right, I guess that wasn't the case. But anyway, Paul, and anybody, if you want to say something, just unmute yourself and speak up. Let's make this interactive.
Yes, please do so. The NAT requirement was met partially from my point of view, because you implemented that on the router, and there are not many other ways to do it with this construct from my point of view, or with native construct. It is quite difficult to do this with available with today's available solutions that are in virtual WAN that you can get there. The segregation, I can talk for Azure and Azure Virtual WAN. This is possible. You said in AWS you can do the same. So I would say we can meet the segregation requirement to do this. When it comes to cost-effective egress for internet, when it comes to a cost-effective solution for internet egress, especially with the requirement where we said you need to filter, for example, FQDNs for software patching. You need to have either an next generation firewall, or use, for example, an Azure firewall within the virtual WAN hub, or the corresponding pendant to this in AWS, the AWS firewall, I think. So this will this is, I would say, partially met because you fulfill the requirements, but it's not that cost effective just for FQDN filtering to deploy, let's say, an Azure firewall or even a next generation firewall. Protection against crypto mining, for sure. If you deploy a next generation firewall, that's one of the things it can be done. The full multi-cloud visibility, you're getting isolated view into both clouds. So this is not really possible. So from my point of view, this is not really met. So what we're seeing here, it is, of course, most of the things, or many of the things, are possible to achieve, but they're quite cumbersome to achieve with the cloud native tools. Also, we haven't digged into the drawbacks that you might face in regards to, for example, any troubleshooting, or even when we come to scale or something like this. This is all not something we've been talking about, but this is something you will discover if you move further and go down the road and explore the solution deeper. There are many roadblocks that you'll still see. So let's go on and let's see how we can solve this with a native Aviatrix solution.
Just one quick comment on the chats. We have Tommy, who posted a link to the description of the service for NAT rules on Azure VPN gateway, virtual WAN VPN gateway. Can you talk briefly to it on how would that potentially be good for the overlapping IP scenarios?
Well, technically, as I mentioned before, you can implement this, but this was first of all mean you need to build an IPsec overlay on top of the ER that you have, which is technically possible. And again, there are some things that you can do. For example, you can say, I have a source NAT, I have a DNAT. So you have certain things that you can implement. And it will, for this simple case where you only have a mapping of, let's say, an existing class /24 network that you're going to map to a single IP, or to map to a single range, it will work for sure. does it scale if you have multiple customers? It might get quite interesting and nasty, especially if you move down further the architecture and see how this plays into the segmentation area, where you might depend on information from the network itself. So yes, again, technically you can meet this when you build an overlay and then use the NAT rules that are available with the VPN gateways. But again, it might introduce some other drawbacks here.
All right,
thank you for the explanation. So, but it's not working with ExpressRoute, I guess. So it's only possible with VPN.
It will work, but you need to build. But you need to have a strict control of your routing, which goes into the tunnel, and so that you only allow the IP address ranges of the on-premises VPN gateways or VPN devices, and then you need to ensure that you're not propagating the not translated range. Instead, you need to build the IPsec tunnel on top of it and propagate there the not translated range, and Azure will take care of it. Basically, you can do it directly on-prem because there's so many things you need to fulfill.
Yeah,
it might be easier then.
Yeah, I think so. Yeah, thank you.
You're welcome. Okay, any other questions or comments?
Let's move on to the next part, I guess, Gerald, for the sake of time.
Okay, Maxime, please go ahead. I'm going to stop sharing now.
All right, so let's go with the solution and the architecture proposed with the Aviatrix platform and how it maps the MCNA model with the three layers that Gerald depicted before: the application layer, the transit layer, and the access layer. And we will try to tackle the requirements one by one. So first, the first one, architecture built as just to remember, prod and dev in AWS and Azure, customer A and C connected to Azure via ExpressRoute, customer B to AWS via the DX, data center connected to high speed to AWS with a 10 gig DX. First of all, what you have to do is to configure your control plane. And what is the control plane? You have to spin up a management VPC or VNet, and you have to configure your controller and your copilot inside. That way, you will have your control plane, and your control plane will be able to configure your data plane. Just because I assumed that there were more customers in Azure, I located the management VNet in Azure and not in AWS, but it's a design decision and it's your choice. Second step in the architecture build, configure the transit backbone. What it means that you have to configure the transit VNet in Azure and transit VPC in AWS. And then once you have done it, you configure the Aviatrix transit gateway. As you can see here, they are in high availability mode, and meaning that they are redundant from each other and they are full mesh. What it means that between each pair of transit gateway, you have 4 IPsec links, and they are all active, meaning that they are all forwarding traffic. Next step, you configure your Spoke VPC VNet, and inside you configure the Aviatrix Spoke gateway. Again, they are in HA mode for the sake of resiliency, but you know, it's a design decision after all. You have production, you can have 2 Aviatrix gateway in HA, and if this is for dev and you want to rationalize the cost, maybe you can just make the decision to have a single Aviatrix Spoke gateway. And you associate this Spoke gateway to the transit gateway, And again, this is IPsec in active mesh, meaning that all the links between the spoke gateway and the transit gateway are active, and they forward the traffic. Once you have done it, let's go to the access layer. And you will understand why in the access layer you need some customer spoke VNet. It will be because of the requirement number 4, which is because of the overlapping CIDR. For the sake of standardization, I have proposed as well to configure a customer B spoke VPC, but as the customer B does not overlap, if you want to rationalize for cost reason as well, you can link directly the customer B to the transit. It's possible as well. And again, I made the decision to have a HA spoke gateway. Then once you have done it, you just have to link the customer spoke gateway and the transit gateway to the on-prem. So for the customer spoke gateway, it will be what we call site to cloud between the customer spoke gateway and the customer themselves, which consists in having BGP over IPsec. The only difference is when you have to link the data center to the transit. Here we need high speed, meaning that it needs to be encrypted in IPsec. That's why it's BGP over IPsec. But you have a 10 gig DX link. And if you do site to cloud or something with the regular native construct, it's absolutely not possible. So that's why you have to configure what we call secure edge in the data center. And secure edge is the virtualization Aviatrix software on VMware. And that way, with that, you're able to have HPE, high performance encryption, and you can encrypt at nearly line rate, meaning that for a given 10 gig links, you can have up to 9.6 gigabit per second over IPsec. So I think requirement number 1 as well is fulfilled. Then let's go for requirement number 2, need of routing control for incoming routes from the customer. In Aviatrix, when you run BGP on the Aviatrix gateway, you have something which is called BGP route approval. Okay, so you need to control the BGP routes coming from the customer, and so do it. And how BGP route approval works, your partner or your customer sends BGP routes to the transit or the spoke gateway that runs the BGP process. This gateway, Aviatrix gateway, reports the new routes to the Aviatrix controller, which notifies the administrator via email that new BGP routes arrived. The admin has to log into the controller to approve this new BGP route. And if this is approved, the controller programs the new routes to the spoke gateway. And this is software-defined routing. You do not have to take care of any routing. The controller does it for you. So requirement number 2, fulfilled. Requirement number 3, it's quite a simple one for Aviatrix. Why? Because you have IPsec everywhere, and it's by default, meaning that when you associate spoke to transit, IPsec, when you do site to cloud or HPE between the data center and the transit, IPsec. When you do some transit peering between the transit gateway in Azure and the transit gateway in AWS, IPsec. What it means, the bottom line is, when you're in the cloud, you have IPsec everywhere. And when you leave the cloud to the customer or to the data center, you have IPsec. Requirement number 3, fulfilled. Requirement number 4, customer A and customer C have overlapping IP CIDR, as you can see, 10.16.1/24 for A and C. And that's why we have added the customer spoke VNet with this associated Aviatrix spoke gateway. And we have something what we call custom source NATing. And you configure the custom SNAT in the spoke gateway towards the production workload, because they will have A and C will have just to reach the production spoke VNet. It means that the spoke gateway, they hide the 10.16.1/24 for customer A and C, and they instead replace the source IP address or the source CIDR to the private IP of itself, meaning the Aviatrix spoke gateway. So requirement number 4 fulfilled. Requirement number 5, I called it segregation, but in fact, this is segmentation. Customer A and C can only access the production workload, meaning the gray one here. Customer B and data center, they can access the 2 workloads. And customer A, C, and B, they cannot communicate together. So we have a 4-step process in Aviatrix for the segmentation. You have to configure what we call security domain. These are the segments. These are logical containers within everyone can communicate. But when you leave your segment to communicate to another segment, you have to configure some connection policy. So the solution was what? The solution was a dedicated segment or security domain for the production VNet and VPC, a specific segment for the dev VNet and VPC, and each customer falls within a dedicated segment. Once you have configured all of your segments, which are represented by different colors up there, because A and C has to communicate to the prod, you have to configure connection policy between the prod segment and A, the prod segment and segment C. And you have to do the very same for prod to B, prod to the data center, dev to B, and dev to the data center. That way, you're safe. Customer A, C, and B cannot communicate to each other, but customer A and C can communicate to the prod, B and data center can communicate to prod and dev. Requirement number 5 fulfilled. And just a bit of a drawing how you can see the segmentation you have configured in the Copilot. In that example, you have 3 different segments represented by 3 different colors, and you can see who is associated to which segment. For instance, the spoke 1 and 3 in Azure are associated to the green segment, and so on for the blue and the red segment. And inside the circle, you have what is called, and what I depicted just earlier, the connection policy. And that way, in our example, everyone can communicate to each other. Requirement number 6, cost-effective egress internet solution. So for the sake of being cost-effective, my solution is to configure dedicated egress Aviatrix gateway for the FQDN filtering in a centralized fashion, meaning that you spin up this dedicated egress gateway in the transit VNet and in the transit VPC. And that way, for the private workload needing an access to the internet for software patching, for instance, no problem. You have the FQDN, which is a domain name list. You can allow or deny, and you can do it for any TCP UDP protocol based. So it's not just HTTP or HTTPS. Requirement number 6, done. Protection against the crypto mining. That's quite simple. It's embedded with the Copilot. We have a tool, a feature which is called Threat IQ and Threat Guard. It automatically inspects, visualize, alert, and enforce the malicious IP, the bad guys. You can see here how it works. The Copilot has an embedded threat database which synchronizes with Proofpoint threat database every 6 hours by default to know the new malicious IP. In the meantime, any Aviatrix gateway report via NetFlows to the Copilot the traffic for the inspection. This is what we call threat IQ. The Copilot compare the traffic and the IPs to his threat database. And if there is a malicious IP, it reports an alert and a notification. This is the threat guard part towards email. And then automatically, the Copilot blocks the malicious IP by enforcing some drop rules in the Aviatrix gateway that has reported this malicious IP. Requirement number 7, I guess, it's fulfilled. And some screenshots you can visualize in Threat IQ where your malicious IP come from. You have here, it's depicted in red, what are exactly the malicious IP, to which workload in your cloud infrastructure was targeted. So I will just quickly annotate so you can see that this IP was targeted and this IP is the malicious IP and which gateway has reported this flow. Okay, so let me clear quickly up. And then what ThreatGuard does in both directions, it blocks the malicious IP with the layer 4 stateful firewall embedded in each Aviatrix gateway. Last one, multi-cloud visibility. Again, embedded in the Copilot, we provide a large set of tools for that. You have the flow analysis with the flow IQ, where you have the top talkers. You can report it to the application owner and the developers if they need some insight regarding their application, the duration of the flow, what was the throughput, etc., full of good insight for the application and dev guys. You also have one tool that I really like, which is AppIQ, where you can have some insight regarding the latency between each Aviatrix gateway. So for instance, you try to simulate a flow between an instance A to an instance B, and just you want to see what is the latency in between. You can have it with AppIQ. On the right side, you have AppIQ with flight paths, which test every construct, native construct and Aviatrix construct, to see if they are properly configured between A and B. And if one of the constructs fails, flight path reported to you, and you just have to click on the link and you directly are redirected to the web portal of the public cloud, and you can on the fly change your configuration to have a good connectivity. Here with this screenshot, the Copilot reports to you in real time what is the health of your cloud infrastructure, and you can see that here some links are down. So it's a first level of troubleshooting. You also have embedded tools like packet capture. It has never been that easy to do some packet capture. You start, stop, and then you go to Wireshark to analyze your traffic. You also have topology replay. Let's assume that a Friday, your cloud infrastructure behaves like a charm. Monday, you come back and your cloud infrastructure is a mess. So you go to topology replay and you can see the change that have been done during the weekend here. Okay, you can see 6 changes. So maybe someone in the weekend did some bad configuration, and that's why your infrastructure is a mess. And voila, what you have before, what you have after all the 8 requirements have been fulfilled. Difference between the two cloud infrastructure. Positive outcome, you have a standardized architecture, standardized operation, day one operation, automation and provisioning, day two operation, meaning multi-cloud visibility. With the transit gateway, you can do some network segmentation. With the sport gateway, you can overcome the overlapping IP challenge. You have cyber threat protection against the bad guys with Threat IQ and ThreatGuard. High-speed connectivity over IPsec with HPE and Secure Edge. Full encryption at network level. By default, you have IPsec everywhere. You were able to control your incoming routes from the customer with BGP route approval. And you had a cost-effective egress filtering solution with the dedicated Aviatrix egress gateway. Last thing, if you have to have a take of all of this design exercise and what is the Aviatrix business value framework, standardized architecture help you to reduce the complexity and repeat your configuration across the region, across the cloud, which means faster time to market and faster cloud adoption. Second take, standardized operation. With the standardized operation, you can bridge the skill gaps. You can diminish and reduce the outage and the business risk. And it leads to what? A reduction of the operational cost. So two things, standardized architecture, standardized operation. This is the key to a good cloud network and security architecture. And here, if you want to know more, please do not hesitate. We have some tech talk. You can schedule some one-to-one session with our solution architect. You can go and try to you spend some time to get certified. We have different level of certification with Aviatrix, the associate level, the professional level, and the design expert level as well. And that's it for today on my side. Any question?
I would only quickly add that everybody can now see the pool. The attendees can see the pool. If you could provide us with your feedback, that would be very, very valuable. We're doing those sessions for you. So we want to make sure that you get the most out of the time that you spend with us. So I appreciate everybody's answers. Thank you.
Thank you, everyone. Really appreciate. That was really insightful. Thank you. Bye.
Thank you also from my side.
Thank you.